Hi, this is engine pump cover of a motorcycle. One of the viewers sent me his 3D scan file for doing the reverse engineering, and he wants to make a 3D print version. So if you look here, it's centrifugal pump and it has 3 mounting points with the M6, and there are also 2 guided pins because the hole that used for mounting this is oversized, that they require to have a guided pin here so that the impeller won't be crashing with the housing of the pump. Usually the centrifugal pump like this, it has a very narrow clearance between the impeller and the pump cover. This is the inlet pipe and exit through this pipe. Okay, the materials that made this pump cover is aluminum, and after I do the reverse in the Autodesk Inventor, I will have to simulate for the deformation of this cover because the pressure inside of the pump is usually around 10 to 16 psi. I need to make sure that the mounting face of this pump is not deformed under the pressure because as you know, the water can leak out. And I will also simulate for the strength of the mounting holes because the initial force from the M6 could be around 90 kilograms per bolt. That would be the force that used for pressing against the gasket so that it can seal the liquid inside of the engine. Okay, this is in a FreeCAD. The viewer has tried to model this part using FreeCAD. He done it until this point, finished the outer shell, and he got stuck in here, not be able to complete the model. From what I see on the geometry of this part, you can actually model this with FreeCAD. It has an additive pipe command that you can sweep cut the channel of the flow from inside of the pump. But I think it would take a very long time to model this part. I don't have that much of the time as well, so I will model this part in the Autodesk Inventor because I can do this in about an hour. But if I use a FreeCAD, it's going to take me longer time, much longer. Okay, this will be the point cloud sent by the viewer. This viewer is the same one who sent me the valve cover in the previous video. So I believe that he still used the same 3D scanner RiverPoint Mini for scanning this part, and I believe that the issue is still there. Okay, let's take a look at the quality of the scan. So I have already aligned this mounting face to the XY plane. So if I click on the side view, so this face is aligned to the XY plane. So I will take a look from the bottom side. Okay, this is the bottom side. If you look closely at the mounting holes, there's 3 of them. You can see that the walls that make the holes, it has a very large thickness. And if I measure the discrepancy of the scan just for this hole, it's gonna be 0.28 millimeters, about 0.3 millimeters. So the center of the hole, when I reverse in CAD, I'm gonna use a 3-point arc. So it could be anywhere plus or minus 0.3 millimeter in this area. And you have 3 holes in total. So the other could be accumulate up to 0.9 millimeters. You probably can fit the bolt into the holes because the hole is oversized, but the original designer that designed this part to have a guided pin. There's 2 positions here because the impeller of the centrifugal pump has a very small clearance to the cover, and it needs a guided pin to be fixed in the correct position. Okay, and if I slice the point cloud into a very thin layer, let's try a very thin layer like this. Okay, this is about 0.4 millimeter. You can see that the wall line is not clean. See here, it's not clean, and some part it has a double layer. So this video is a case study to see if we can actually reproduce with the 3D printed engineering plastic. So I will continue to use this 3D scan even though it will not fit to the engine. Okay, here's in the Autodesk Inventor. The first step is that I trace the mounting face of the pump cover by slicing the point cloud into a very thin layer and use the arc lines to trace it. And then I just extrude it, so we have a solid block here. And next I flip it to the bottom and tracing the inner wall of the cover, and then I use the extrude cut to cut it into this point. So if you look from the side view, this will be the highest point of the inner shell. Okay, next, this is an important part because I have to cut the flow channel of the centrifugal pump, which is this flow channel is in a spiral, and it also has variable profiles. So this part is narrower, this part is wider, and this part is deeper, this one is shallower. So to make a profile cut of this part, I can do this by using a loft command, loft cutting, and I have to do multiple loft, and I need to create a sketch for each angle because I cannot use the coil command. The coil command in the Autodesk Inventor, it needs to has constant profiles, but this one is variable, so I cannot use the coil command. I can only use the loft command. So I need a shortcut to get this done fast because I want to model this part within an hour. Top view of the flow channel. So I will cut it in a step, 0.5 millimeter per step. Okay, let me show how I do this. Okay, this is the first step of the cut. And next I create another sketch, and I create a line here. This line will be the starting point of the next step. And the second step, I cut it for 0.5 millimeter. Maybe you can see this. So each step is 0.5 millimeter. And for the starting point of the next step, I will use the point cloud to see which is the location when it starts to decline. So what I do is I keep doing this until it reaches this point. So each step here is 0.5 millimeter. So I can do this quickly without creating sketch profile for lofting. I have a steps for the flow channels. Okay. After that, I eliminate the step by using a chamfer. So I chamfer it 0.5 millimeter deep, and I drag it along the length of the step. So if I keep doing this, it will smooth out the channel, and I can do this within less than 10 minutes. This is the hardest part of the centrifugal pump. Okay, because a centrifugal pump, when you use a coil command to sweep cut, you can use it, but the rotation axis of the centrifugal pump is not fixed. The inner wall of the pump is not circle. This part is not circle, so the center of the axis will move. So this is the fastest way that you can reproduce the geometry of the flow channel of the centrifugal pump. Okay, and next I create an opening for the outlet and just extrude cut it. Okay, I add a fillet here so that the flow will go smoother. And if you can see here, maybe you can. Yep. The original designer, they add the wall thickness in this part, but I'm not going to do that. It's blocking the flow. I will add the thickness on the outside of the pump instead, so that it will flow better than the original part. Okay, next I'm going to make an extrude cut. It will create a ellipse here along mounting face, and then I extrude cut for the mounting holes of the bolt. Second cut, the two mounting holes here is shorter than the first one. And next I create a circle cut. This would be the inlet chamber of the cover. So I will make a cutting until this point using the point cloud as a reference. Okay, next the outer shell of this cover, it has a spiral shape. So this time I will use a coil command to create this sketch. You see this sketch is just a rectangle, and I use the coil command to sweep cut this sketch on the outer shell. So after I cut with the coil command, the outer shell we have a spiral shape like the original one. The cutting will end here. Not doing a full rotation cut. And next I'm going to extrude the remaining of the top cover. And next I make another extrude here. Okay, let me change the color. It's better to see like in the gray color. I make a fillet here and another fillet here. And next I'm extruding the hole for the outlet. Okay, next I create a sketch here for the inlet chamber, and I will revolve it using this axis. Okay, this is the revolve command that I use to create this inlet chamber. And then I use another revolve to create a volume inside. Okay, next I start to create the inlet tube. So I keep extruding for the inlet tube. Okay, and I use revolve command to revolve the profiles of the hose fitting and the stopper. Then I use the extrude command to cut a hole. Diameter is 15 mm. Cut a hole through the inside of the shell, and here's a stiffener for the inlet. Okay, and next I do the same for the outlet. Outer diameter is 20 mm, and I use a revolve command to revolve the profiles of the hose fitting. Okay, next I create a hole by using arc for finding the center of the hole. This is the issue that I told you earlier in this video. The location of the hole, it requires that the 3D scan data has a sharp edge of the hole. If the edges of the hole is not sharp, trying to locate the center of the hole could lead to large error. Okay, and then I try to locate this to guided pin, the hole for the guided pin. Okay, so that's it. This part is not for a beginner. You need some CAD experience to model this part successfully. The command is quite long, and you need a reliable CAD software that can process this part to the end. Okay, let's move on to the simulation. Okay, this is a simulation menu. I will start by assign aluminum as the material of this part. So here I apply 16 psi pressure on the inside of the wall. This will be translated into 0.11 megapascal of the pressure. And for the support, I placed 3 support on the edge of the mounting holes so that we can see the stress and deformation with the original part. I'm going to run the simulation because it's only 16 psi, which is not much. If you inflate your tire, it's going to be like 30-35 psi, but the pressure inside the coolant is not that much. It's just 10 to 16 psi, so that the stress on the shell is very low, only 15.8 megapascal. So any plastic will have the strength to hold this pressure, but the failure of the structural part is not confined to the strength. It can be failed from deflection as well. So if the deflection is too high, the mounting edge here is gonna lift up and the water will leak out even though you have a gasket underneath. So let's take a look at the displacement. So if this part is the aluminum, this one is exaggerated, so you can see where the part is lifting. And this point here is only 7 microns. So with the original aluminum part, it will not leak with the 16 psi pressure because it's very stiff, only 7 microns. Okay, next I'm going to replace this material to polycarbonate. Here, polycarbonate, and I will rerun the simulation again. Okay, so we have polycarbonate. The stress is only 13.9 megapascal. So I can print this without breaking because the pressure is not that much. And when we take a look at the deformation, you can see that this is the orange color. Okay, because polycarbonate is quite stiff, and if you look at the color plot here, it's somewhere around 0.1 millimeter in this point. 0.1 millimeter, it could leak the water because 0.1 is quite a lot. I mean, comparing with the aluminum is only 7 micron. Now we have 100 microns here with the polycarbonate print. But if I use something like PETCF with the carbon fiber, the number of the displacement will be cut by half because the PETCF, it has a Young modulus of 4.5 gigapascal, while the polycarbonate has only 2 gigapascal. So if I use the carbon fiber reinforced filament, this part could work, but the user need to choose the one that is also waterproof. I think PET and polycarbonate is waterproof. From this simulation, the strength is passed, and deformation with the carbon fiber one, it could work. So I don't see why it will not work. The thickness of the wall of this part is somewhere around 3 millimeters, which is quite okay, I think, for the 3D print. And if the temperature of the coolant is not over 100 degrees Celsius, then this pump cover could be used for replacing the original part. Okay, let's move to the second simulation. It mounts with the M6 bolt, and M6 bolts, when it's thread into the aluminum female thread, it's gonna apply initial force somewhere around 90 kilograms for the M6 on the aluminum thread. So I apply 90 kilograms on the mounting face of the bolt, and I believe that I assign polycarbonate for the materials. And when I click on the simulate, I'm gonna check on the stress. Okay, so the stress on the mounting face of the bolt is 19 megapascal, but for the polycarbonate is 70 megapascal, so it should work. But if you tighten it for a long time, it could be deformed from creeping. You probably need to use a spring washer to maintain the tension from the M6 bolt. Okay, so the strength pass, the deflection pass, and if I print this with solid PETCF, it should work in theory. Because I don't have the engine with me, he sent me the 3D scan file, so after I print this, I wouldn't be able to test fitting this part to see if that will actually work. I'm gonna print this with polycarbonate, and I'm going to turn it like this. And to print this, I'm going to use 100% infill. Okay, so we have something here. I need to block it. Add support blocker. Let's make it smaller. Move it here, move it here. Okay, I don't need support in this point, so I'm gonna block it. Let's slice it one more time. Okay, so it should be good. Let's look at the first layer. Okay, it shouldn't fall, right? Okay, it shouldn't fall. Okay, there is no island far away from the main part, so it shouldn't fall. Okay, 1 hour 38 minutes for the polycarbonate. So I print one with the PIA first to see if the support work, and then I print with the polycarbonate. Okay, let's check this after the printing is done. I use a Kexels K8 polycarbonate for printing. (110°C on the bed and 260 on the nozzles. Chamber temperature is 50°C. It's print a little bit slower than the PLA. PLA takes about 1 hour, and this one is 1 hour and 38 minutes. So this part from my previous video, you can see that the polycarbonate has a very high layer adhesion. So when it breaks, you wouldn't see a layer lines here. It feels like injected mold. Okay, so removing from the epoxy build plate is quite easy. Okay, let's compare it with the PLA. The polycarbonate is a lot glossier, and I have already sanded it. I haven't sanded this one yet, but I will. PLA looks better. Polycarbonate is heavier. See, the step inside here is very smooth for the PLA. I can feel the lines that I used to extrude cut the spiral of the flow channel. But when try to squeeze it, it's very stiff, this one. I think the young modulus for this one is more than 2 gigapascal. I think it's somewhere around 3. But for the PLA, usually it's around 2. But I can squeeze it. It's going to deform a little bit. But this one is quite stiff. And I think the layer fusion is very good, and the water shouldn't be able to seep out from the layer lines. So I have already sanded it. As you can see that the polycarbonate is very easy to sand, as easy as ABS. So if you have a interface with a support, you can sand it out. Doesn't take much of the time. Easier than the PLA for sanding, but the surface is really glossy, so any defects will show up, unlike the PLA. I think this part should work if the hole does fit. I mean, that's the issue with the 3D scanner, not the printer or the reversing process. Okay, this is one of my favorite filament, polycarbonate. In next project, I'm going to make a 3D print with a PET carbon fiber. That one has the stiffness of 4.5 gigapascal. So when it's print with 110 degrees Celsius, a bed temperature, the temperature that you start to deform will be higher than 110. And this part requires no drying, so I can just print anytime I want, same as the PLA. Okay, thanks you guys for watching. I'll see you in the next video.